Here I want to talk quickly about some work I've done looking at proplyds in NGC 2024, which is also known as the Flame Nebula. The Flame Nebula sits here in Orion, so here we have the three stars of Orion's belt, the Orion Nebula and the Horsehead Nebula. So this little bright thing here with the foreground obscuration is the Flame Nebula. Let's zoom in on it. So again, you have this foreground obscuration that divides the region pretty much in two, and you've got stars forming behind it here. Now this is the youngest star forming region in Orion, and we'll quantify that in just a second. So Van Terwesger et al. This year in 2020 undertook an ALMA survey of the region in the continuum, so they could do things like estimate disk masses and fractions. And they found evidence for two distinct populations. So what I'm showing here are Herschel contours of the region. So you've got a dense cloud here, and this diagonal dashed line separates the two populations that Van Terwesger et al. Have discovered. So in the east you have a 0.2 to 0.5 million year old population where the disk fraction is about 50%. And in the west you have a slightly older, roughly 1 million year old population where the disk fraction is more like 15%. So it's severely depleted compared to the east, despite having similar ages. And the explanation proposed was that you have these two strong UV sources. So there's a B 0.5 star and an O8 star here. So the argument was that they work together to evaporate the western population. So there's maybe some clear line of sight here for the O8 star. And that the stars in the east are shielded because they're embedded in this star-forming cloud. So that motivated me to go and look for proplyds in the region, which I did in the first instance just using archival data from the Hubble Science Archive. And lo and behold, there were 8 proplyds sitting there in the region. So one of these had been mentioned before in a conference proceedings, but these were otherwise unpublished. So this is again the region. You've got the Herschel contours, you've got an optical image on top, and this diagonal line is the same one from Van Terwesger et al. 2020 with the younger, higher disk fraction population over here, and the slightly older, very depleted disk fraction population over here. And so yes, we found 8 proplyds, 1, 2, 3, 4, 5, 6, 7, and 8. And here is IRS1, the B star, and here is IRS2b, the O8 star. So what are the implications of these proplyds being found? Well, first of all, there is definitely photoevaporation going on in the region. But some other implications are that we have evidence to show that IRS1 is very much responsible for the photoevaporation in this depleted region. So the reason we can say that is if we look at the two proplyds nearest it first, they are clearly pointing towards IRS1. So these cometary proplyds that we've been able to see in the Orion Nebula cluster for decades now, they are pointing towards the UV source responsible for evaporating them. You can see that clearly happening here. And the proplyd 2 sits up here off the top of the image, but is still pointing towards IRS1, despite being closer to the O8 star. Than proplyd 1 was. So we can say that the B 0.5 star IRS1 is causing photoevaporation in this region. And the other interesting thing is this detection of a whole bunch of proplyds in this other region where we were saying there is a higher disk fraction. So the picture we expect is happening here is that the star-forming cloud is gradually getting evaporated away itself by the O star, and as it does that, the stars gradually and sequentially get exposed to the radiation and then very rapidly dispersed. This is 0.2 to 0.5 million years old on this side of the line here, and more than half the disks are gone. So this is very interesting as well. It shows that evaporation can happen very quickly, and it also shows the importance of embedding stars for as long as possible, giving them a chance to try and produce planets in these kind of hostile environments. So there's obviously way more to talk about here, but we can't do it in 5 minutes. So look out for this paper, which has now been submitted to MUNRAS, and there'll be much more to find out there. And you can also discuss with me